Welcome back to the course, Multilayer Neural Network Training and Testing Implementation. This is Lesson 2, where we will discuss in detail the structure of a multilayer neural network. In this lesson, we will look in detail at the structure of neural networks and the computations that take place at the neuron layers and at the neuron level. We will first look at the structure of neural networks that we will use for the remainder of the course. This discussion will pick up from where we left off in the previous lesson, and we will provide more detail. For efficiency reasons, computations are typically performed at the entire neuron layer at a time rather than at the neuron level. The computations are presented at the single neuron level. However, in the code, the computations are performed at the neuron layer level since they become matrix operations at the layer level. In the previous lesson, we ended up presenting and discussing this diagram, which depicts a neural network as a layered parametric function of x. The input x is progressively processed through the layer's parametric functions, where the parameters are the weight matrix, bias array, and activation function. We'll take a more detailed view of this structure in the next diagram. This is the most important diagram of this course, and it shows in detail the complete structure of a multi-layer neural network. As you can see, each layer has a set of connection weights and outputs. The first layer, layer 0, is connected to the n inputs x, and the last layer produces the m outputs y of the neural network. The m outputs are compared to the m targets for a given input vector x to calculate a prediction error. We will be using this structure of a multi-layer neural network for the remainder of this course. In this slide, we will take a look at one neuron layer which has the label or index lowercase l. By definition, the neuron layer will have n sub l neurons. The neurons are indexed using the letter k by convention. Each neuron in any layer is connected through weights to the outputs of the previous layer or to the inputs of the neural network. They represent the inputs to the layer. These inputs are indexed using the letter J by convention. The layer's composite connection weight matrix is labeled W superscript L. Each neuron produces an output labeled A superscript L sub K. If this is the last layer of the neural network, the outputs represent the outputs of the neural network. Otherwise, they will become inputs to the next layer of the neural network. We will now look specifically at an arbitrary neuron K in layer L. The inputs to the neuron are labeled as A superscript L minus 1 sub J, with J going from 0 to n sub L minus 1 minus 1. Each neuron in a layer is connected by weights to the inputs to the layer, which are either the inputs to the neural network or outputs of the previous layer. Their corresponding weight is labeled W superscript L sub K comma J. Notice that the weights belong to the neuron of this layer L, not to the neuron of the previous layer. In addition to the weights, each neuron has an associated constant called the bias for the neuron. The bias is labeled B superscript L sub K. In order to calculate the neuron's output, we first sum the multiplication of a weight by its corresponding input, and then we add the bias. For simplicity, the result of this operation is assigned to a variable labeled Z superscript L sub K. The value Z is often referred to as the net value. This net value is then passed to an activation function labeled alpha superscript L to compute the neuron's output for a given input vector. The output from this neuron is labeled A superscript L sub K. Note that the activation function is specific to this layer. Each layer can have its own activation function, or all layers can use the same activation function. As was mentioned previously, although the computations are best viewed at the neuron level, it is more effective to perform the computations at the neuron layer level. Doing so makes the computations use matrix multiplication, which can be performed much faster and for real-world applications can use specialized hardware to perform the computations. In the next lesson, we will be using the structure of the neural network presented in this lesson to discuss how the neural network is trained.